Hi everyone, this is Wesley Cotomy from Cal Poly, and I will be presenting our work on self-supervised Poisson-Gaussian denoising. This is a joint work with Sonia Rao, Claire Minerath, Guy Hagen, and Jonathan Ventura. First, I will discuss some motivations for our work. In fluorescent microscopy, imaging under normal or intense light conditions may damage or kill living cells. Thus, images must be acquired under low light conditions. Unfortunately, this results in images that are corrupted by a high level of Poisson-Gaussian noise. So, to recover a clean image, we must use denoising. Lastly, because the organisms are moving, it would be difficult to acquire corresponding noisy and clean images of living cells to train a denoising neural network in a supervised fashion. Therefore, we adopt a self-supervised training strategy, where our goal is to learn how to remove Poisson-Gaussian noise without having access to the corresponding clean data. In our work, we use the blind spot neural network proposed by Lane et al. This network learns to predict a distribution for the center value of a noisy image patch from the surrounding neighborhood of noisy pixels. We use a Gaussian distribution as our prior and select our noise model to be a Poisson-Gaussian distribution. Then we train our neural network to maximize the marginal distribution of the noisy pixel. Our first contribution is an extension of the blind spot neural network to handle Poisson-Gaussian noise. We input a noisy image into our blind spot model and produce a per pixel mean and uncertainty that represents our Gaussian prior. We also output the per pixel variance of our Poisson-Gaussian noise model. To handle Poisson-Gaussian noise, we train our network to minimize our newly proposed loss function. A full derivation and explanation for this loss can be found in our paper and supplemental material. Because the prior uncertainty and noise level estimates are interchangeable, we need to add a regularization term to our loss to encourage the prior uncertainty to be small. In practice, we found that the choice of lambda strongly affects the results. This led us to propose our second contribution, which is an uncalibrated model that removes the need for regularization and hyperparameter tuning. In our uncalibrated model, we input a noisy image to our blind spot neural network and produce a mean and total uncertainty estimate at each pixel. The total uncertainty accounts for both the prior uncertainty and noise estimate that was required as output in our previous model. Now, we can train our blind spot neural network by minimizing our uncalibrated loss function. Rather than having the network learn the noise parameters, our uncalibrated model allows us to defer estimating noise parameters until test time and removes the need for regularizing the prior uncertainty. At test time, we run the blind spot neural network with a noisy image to obtain a mean and total variance estimate at each pixel. Then we use a bootstrapping technique where we let the mean estimate, mu, act as a pseudo-clean image. Using our pseudo-clean image and noisy image, we estimate the noise parameters by fitting a Poisson-Gaussian distribution. Once we have the noise parameters, we compute the prior uncertainty from the total uncertainty and noise estimate. Finally, we obtain our denoised image by computing the posterior mean estimate. Now we will take a look at some of our results. First, we have some results on the confocal fish and 2-photon mice datasets from the FMD benchmark. For each dataset, we show a single test image and report the average PSNR over 50 test images. Looking at the pseudo-clean images, we can see that some noise still exists in the denoised estimate. In contrast, the denoised images from our uncalibrated model are much cleaner and sharper. This improvement in denoising quality is further supported by the difference in average PSNR of the pseudo-clean and uncalibrated images. Next, we take a look at a comparison between our regularized model and our uncalibrated model. Looking at the performance of the regularized model for each dataset, we can see that the denoising quality varies greatly depending on the value of lambda. We also see that a different setting of lambda is optimal for each dataset, which indicates that hyperparameter tuning of the regularized model is critical for obtaining good denoising performance. On the other hand, our uncalibrated model does not require any hyperparameters, and outperforms the regularized model at any setting of lambda. We also compare our model against other self-supervised denoising methods on a benchmark dataset provided by Prakash et al. Our uncalibrated method is able to obtain cleaner and sharper denoised estimates than both noise to void and the bootstrap histogram model. While our method obtains similar results to the bootstrap Gaussian mixture model in terms of sharpness, it does a better job at recovering fine details in brighter regions, which can be seen in the mouse nuclei example. Here we have some more comparisons on the FMD benchmark. In terms of PSNR, our uncalibrated model outperforms other self-supervised denoising methods on all three datasets. Please see our paper for comparisons to self-supervised methods and more evaluations on synthetic data. Thanks for watching.